Hi, let's work in tutorial 7. So we are leaving the bubble of the foundations. Now we focus more into the turbulence modeling. So you have tutorial 7 here. Okay, you can download the mesh, also download additional data. We have validation data there. So basically this is a classical turbulence model case. So you click in the link, you will go to this NASA website. So you have a lot of data here that we took for the validation, also some experimental profiles. So also in the data that you will download, you will have this file with the experimental data, but these are also two inlet profiles. Okay, so from the experiments we have that data that then we're going to see how to read data to input inlet profiles. So first we run the uniform profile, and then we use an inlet profile, and let's see the influence of that. So this is the mesh that we have, and let's do the standard case setup. So as you download, you go there, general, let's work, pressure base, steady, you go to models, no energy, and then we are here in the tab of viscous model where we select all the turbulence models. Okay, so in this case we're going to use a K8 zone, realizable, enhanced wall treatment. Remember that this is for wall resolving, but feel free after this one to play with all these tutorials. See that this in theory should be a fine mesh. Okay, so let's see what we get here is we are wall resolving. Okay, so after you choose this, nothing else in the models tab, then we go to materials. We have our working fluid that let's choose air, the standard practice, the standard properties. In cell sun, we go here, and this is, remember to choose if you have different fluids or solid regions, or to add eventual source there. So nothing to do there, defaults are okay. And then we go to boundary conditions. So let's set boundary conditions in this case. So we have an inlet here, velocity. Okay, so in this case we have the value already here. Okay, so this is the value that we need to set here. Okay, 38.7. Then okay, we know the diameter here, so you can use this one, or it's up to you to use different values. So but let's use these values. Then the rest are walls, and then we have the outlet. Remember that in the outlet you need to set also boundary conditions. Okay, so it's a pressure outlet, fixed pressure. Okay, we fix our pressure, and then we give also the specification for backflow turbulence. Okay, in the case that you have flow coming back. So it's up to you. We have addressed this in the course, so you can choose your values. So we choose the default values. Okay, then we keep moving. We go into method. So let's use the default method. Remember what I have told you, that for steady simulations this is the most robust method, so you can go and use it, but you can play around with different methods. Then you have, remember, always momentum. This you need to get second order accurate solutions. Okay, so always momentum second order. And for the turbulence variables also, you can get it second order or first order, or even higher. There is no problem in first order. However, second order accurate sometimes will give you a slower convergence rate. Okay, so here it's not a problem if you put a first order win. Okay, remember, turbulence is diffusion, so somehow you will enhance in diffusions, but you feel free to play with second order and see the convergence rate. Solution shouldn't change a lot in this case. I will leave it the default proposed by Fluent, by the way. Then controls, we get also default values, and reports definition. So let's talk about setting values here. So remember, I always like to set the y plus average. In this case we have it on walls, in all walls in our domain. So you click and then you set your monitor. Okay, and that monitor also I wanted to plot it, so you choose to plot it. Then I computing the wall shear stresses just in the bottom wall. Okay, so we have the shear stress here. Okay, so I will compute shear stress in that wall, so it will be area weighted average, wall fluxes, and the wall shear stress. Okay, so here we have the magnitude. Okay, then we have this quantity that also have the area weighted average in the outlet. Okay, so I want the automatic average of the turbulence viscosity ratio. So I just want to compute another quantity, okay, to monitor. Residuals leave standard values. Well, in this case, I reduce the continuity a little bit more just because I know that it will converge fast. So this is what I was we're talking about, that it's not a good idea just to leave the default values, because it will stop here when it reaches this convergence criteria, which is a good criterion. But however, you will see that your quantities is still isolated. So I will do it like this, and let's see. So these are created automatically when you define your report. Nothing else to do, and then let's do some initialization. Okay, so I will initialize with this value. So these values are computing for the values that we have here in the inlet. So I will go here, initialize, and we have initial conditions. So we can go and we can already start from here, but let me show you a very initialization method. Okay, because so far what we have, everything uniform in the domain. So remember that you can improve your convergence rate and also the accuracy of your solutions. You have much better initial conditions and also boundary conditions. So as you go to the text using interface, you will see that here is you go to solve, then you press enter and you will show more of the options. If you want to go back one level, press you type quit or use Q. Okay, so you go solve and then we go initialize. Okay, you can put just the first letter and you enter, and then you have the options, and then we have this option FMG initialization. This is a very good, I really like this method. Press yes, and we'll do basically one multi-grid iteration and we'll find a very good initial condition. So now as you visualize, remember previously it was uniform, but look at that. Now we have this, which is a remarkably good boundary condition, initial condition. See that at the walls, everything. Okay, so I highly recommend this method to use it. Not always you can use it, you have limitations. Okay, you can only use it when you have a steady solvers. Okay, you cannot use this if you have on a steady, but simply just choose that option, steady, initialize, and then change it to unsteady. There is no problem. And then also there are some limitations, probably compressible flows. Probably if you have closed domains, also it makes no sense to use it. Okay, so in this case it worked fine. So now let's go, and I think we're ready to go. Okay, so put 100 iterations here, time scale factor 1, and let's calculate and let's see what we have. Okay, so remember this is the first iteration that we're doing with uniform inlet here. So let's see what we have. Okay, I will press calculate and let's see our final solution. Okay, so look at what we have then. In my case, it converged in 26 iterations. That is really good, okay? And probably if you are new in CFD, you will say, okay, probably will stop here. But remember that this is why I say always monitor new quantities. So see that we're quantity this interior quantity, we're monitoring this interior quantity at the outlet. See that it still is oscillating at load, also with shear stresses is still oscillated. So this is why it's not a good idea just to rely on these residuals to assess the convergence of your solution. So in this case, I will do to iterate more. So you can disable this quantity or just reduce this one. Usually continuous is the one that you reduce. And keep iterating. Later when we do the next case, the airflow, I will show you another convergence criterion here. So, and see that now is iterating longer, okay, and see that your quantities now is much better. So now it seems that your wall shear stresses are stabilizing, okay, and this quantity also since that is stabilizing. Still we might run a little bit, so let's do something that we can disable all these monitors, okay, and then I will run just 200 more iterations to be sure. Okay, so let's do this and see what we have. Okay, my case arrived to convergence after, well, didn't arrive, you just arrived to the maximum number of iterations. So look at here what we have. Okay, so see that my quantities are not oscillating anymore, so I can take it, let's say that this is a statistically steady result. Look at the what I mentioned is that no, don't rely on these monitors to assess your convergence. So for instance, this here is you stop, let's say probably at 50 iterations, see that this quantity is still oscillating. But if you check here that at 50 you already have 10 to the minus 4, which is good, really good, but the quantity is still oscillating. So always monitor, remember, monitor additional integral quantities, forces, quantities at the outlet, mass imbalance. So remember, the method is conservative, what is going in is going out. Okay, so for instance, to show here, for instance, remember you have reports, you can a posteriori you can compute many more quantities. So in this case, let's just compute fluxes just to confirm that this method is conservative. So we have inlet and outlet compute and see that the value is small. Okay, so we're okay. So now let's do some post-processing. We can visualize here the solution and see that we have the boundary layer, see that it's developing here. Okay, boundary layer, and we have this recirculations on here. Okay, so depending on the turbulence model that you use, you may have different reattachment points. Okay, so interesting experiment, but we're interested just in computing in comparing the wall shear stresses here in the bottom wall. So to visualize that quantity, we go here, xy plot, xy here. You can create here, in this case I already created, but you can create a new one. You select the wall, so it is bottom wall. We want to monitor wall fluxes, wall shear stresses, and we want this quantity in this direction. Okay, so as you plot, you have it. Okay, so this is the wall shear stress, the magnitude. What I want to visualize x component. Okay, and now let's compare this one with the experimental results. So as you press load, you will have the file, this one, cf data. Okay, save and plot, and here you have. So this is our comparison, and see that we have kind of, maybe we have similar trends, but there is a difference that is probably more, a lot, 50%. So we can do much better. Okay, probably you can try and you will do many iterations, different methods, and you won't get an improvement. Even you will go and you refine your mesh, but you won't get let's say a clear improvement in your solution. So here's a chance when we choose a much better in the boundary condition. So let's use a profile, okay? Because in this case we have a fully developed profile that see that in this case we're given here a uniform profile. So we didn't have enough distance to develop that profile. So that is the influence that we have in this case. So instead, if we use that experimental profile, we put it here and we will get a much better results. So we're going to read a profile file. This is a file. So in my case, I was running the KXL model. You have two files here. So this is the one for the KXL model. As you are using the K omega, you can use this file. And I won't go into details about this file because you can go to the documentation and see how to create these files. But here, basically what you have is the values, okay? X component, Y component, and then the quantity, okay? The components that you give here, the values, they don't need to be coincident with your cell center or the vertex, okay? Or Fluent will do interpolation of those quantities, so you don't have to have, you need to have those quantity matching. Okay, to read that quantity, go into files, you go read, and you have here profile. Choose your profile, and then see that, pay attention that you don't have any errors here. So see that you are reading x, y, x velocity, turbulent kinetic energy, and turbulent dissipation rate. Okay, so now these values are available. So you can plot those quantities. As you go here into results, see that you have profile data. Press here and choose what you want to plot. So I want to plot in the y-axis x velocity and y in the x-axis. Okay, so go here and see that you have your velocity profile. Okay, then let's do the turbulent kinetic energy. See that now you have your profile here, and then you can plot the dissipation rate. Okay, so this profile, So you go in the website, you have all this information here. Even there are many sites that you can get that information. Okay, so this is the information that we have. So now using these profiles, we are going to rerun the simulation. So to apply these profiles in our boundary conditions, we go back, boundary conditions, and we want to use them in the inlet. So as you go here, edit, then here you can use those profiles. So you will assign those profiles here. See that you have this option to expand, and see that you have, okay, see here that you have this quantity. So we can use velocity here, okay? So see that you can expand, you have many options. So you can program a profile here, there's no problem, but we want to use this one. And then we have here available, okay, use that one. Oh, it's not taken, sorry. Okay, use that one. And here we want to use K and epsilon, okay? So you need to change to K and epsilon, and see that now you can access those quantities here. So you have TKA, the turbulent kinetic energy, okay? And then dissipation rate. So you assign your profiles there, and we're ready to go, okay? So let's rerun, we can initialize. So I will use now just a standard initialization, okay? I won't do the full multi-grid initialization, okay? And then let me run. I will run 200 iterations again, okay? And let's see what we have. So always monitoring these quantities. We know that it is going to convert fast, but just put 200 here and let it run until these values stabilize, okay? So let's see our final outcome. Okay, in my case, I drive to 200 iterations, see that all these quantities are stabilized, okay, stable, they are not oscillating, and see your residuals are falling in a monotonic way. Very nice. This is the behavior that we always want, but it's difficult to get. And now we go here, plop, okay, and see that already here we can see that we have different behaviors, okay? So see that this bubble also is different. So let's plot the shear stress. It's very interesting in this one. And we load the solution. Okay. Save plot, and voila. See that we have a much better. So let me put here line, save plot. Okay. That was 1, and we have it for curve 2. Apply. Okay, our solution, experimental and numerical, and see the influence. So here clearly you see, in this case, we see clearly the influence of the boundary conditions. Better boundary conditions will give you a much better agreement. And you can play around also with initial condition, get crazy values, okay? And you will see that, or it might converge to something different, or will diverge, or it will converge to this one as well, but it will take much longer iterations, much longer times. So at this point we did it just for this method. Feel free now to play with all the other options. Okay, that was all for these tutorials. Feel free to play around with this case. See you next time. Bye.